Hello everyone, and thanks for joining us today on our weekly product webinar. My name's Dr. Roberto King and I'm CTO at Foster & Freeman. Before we get started, I'm just going to go through a few housekeeping procedures. To simplify the proceedings, all of our guest microphones are going to be muted throughout the webinar, but please use the chat box to ask questions as we go through, and we'll do our best to answer as many as we can at the end of the webinar in the Q&A forum. So today's webinar is going to focus on trying to get the very best out of your cyanoacrylate fumed evidence. And of course, when we talk about cyanoacrylate, what we really mean is ethyl 2 cyanoacrylate, or as it's generically and commonly referred to, superglue. Now, cyanoacrylate was actually discovered in 1942 by Dr. Harry Coover over in the US, an organic chemist, and he was actually working on developing clear plastic materials for use in gun sights, and accidentally discovered the unique properties of cyanoacrylates to actually bond very strongly and form a superglue, as we use commonly around the world for fixing everyday items. But of course, in the forensic laboratory, superglue, or cyanoacrylate, serves an entirely different purpose and is arguably the most widely used process for non-porous evidence. Within a forensic laboratory, it's common for large quantities of semi and non-porous evidence types to be submitted for examination for finger marks. And these are arguably one of the most common evidence types that enter the forensic laboratories. They take the form of plastics, ceramics, glasses, and other such materials that generally tend to be processed using cyanoacrylate fuming. Typically, the workflow dictates that non-porous evidence and semi-porous evidence, as we've just mentioned, are processed using cyanoacrylate and then imaged and observed under white light illumination to look for any developed finger marks. They can then be subsequently dye stained with something like rhodamine 6G or basic yellow 40 to improve contrast between the finger mark and the background on which the finger mark resides. And the finger marks are then marked up for further examination and image capture. Now, until now, this has been a very time-consuming and laborious process, and of course with time comes money, so it becomes an expensive process to man over long durations. So the typical sequence is to fume the evidence, observe the evidence, look at the evidence after it comes out of the fuming chamber, stain the evidence if required, search it again, mark it up, record the images, and repeat the process where necessary. A lot of work that we've done at Foster & Freeman over the last few years, and certainly since the evolution of DCS5, has allowed us to look outside of the visible spectrum. So we're looking beyond 700 nanometers and at shorter wavelengths than 400 nanometers. Now, in these parts of the spectrum, the camera, or a modified camera in our systems, can see things that our eyes cannot. And this opens up a wealth of evidence that can be potentially missed using visible examination alone. For the purposes of this presentation, we're really going to focus on both reflective ultraviolet illumination, and for this we're talking about 365 nanometer irradiation, so UVA, and reflected infrared illumination. So we're looking at the near IR from about 800 to 900 nanometers. And when you look at cyanoacrylate fumed evidence in these parts of the spectrum, you can often reveal finger marks that would otherwise have been missed or would otherwise have had to been processed with a dye stain, again making the process a lot longer and a lot more convoluted. So in this instance, we're taking the stain part of our workflow out of the sequence and suggesting that we fume, search in both the UV, the visible and the infrared, mark up and record. This naturally allows us to process evidence very quickly, which saves us time and frees up valuable resources in the laboratory. So let's talk a little bit about reflective ultraviolet imaging. Again, UVA, so 320 to 400 nanometers, which we typically refer to as 365 nanometer imaging. A lot of you will probably be familiar with UV imaging that takes the form of UV fluorescence. This is where we illuminate an item. In this instance, we have a bone fragment with a narrowband ultraviolet light source, and we look at the fluorescence that's induced by the excitation from the light source itself. So the bone fragment here appears to glow in the violet blue part of the spectrum. And this UV illumination, searching for fluorescent materials, trying to improve contrast, can be used for a wealth of different forensic applications. But some caveats always remain. We must consider the output intensity of the light source when we're considering and thinking about fluorescence, because of course light intensity is directly related to fluorescence output. And we must also consider the purity of the waveband. So schematically, when we're talking about ultraviolet fluorescence, evidence is illuminated with the UVA light source, so 365 nanometers, and the fluorescence is emitted somewhere, typically in the visible spectrum, from about 400 nanometers onwards. However, we can go beyond fluorescence and start talking about and thinking about the forensic applications of UV illumination in terms of reflectance. So the characteristics of UV are what really make it suitable for the purpose that we have in mind. UV light, when shone onto a surface, is either heavily absorbed or heavily reflected. This allows us to gain contrast between the substrate and any evidence that may be on its surface. UV light also lacks penetration, given the shorter wavelength being used, and it's readily scattered. And it's the latter, the fact that it's readily scattered, that allows us to get some really strong contrast when imaging cyanoacrylate fumed marks. All digital cameras are actually sensitive to both ultraviolet and infrared wavelengths. However, internal ultraviolet and infrared blocking filters are put onto the sensors by the camera manufacturers, allowing us to only see the visible part of the spectrum from 400 to 700 nanometers. Foster and Freeman actually provide custom modified cameras with specialist lenses that allow the transmission and detection of both ultraviolet and near-infrared wavelengths. So let's have a look at some examples of some evidence that's been processed with cyanoacrylate and imaged under reflective UV. Now, if we move to the other end of the spectrum and the near infrared, we can start to consider infrared imaging in terms of reflection and fluorescence. Infrared imaging really started its life within the forensic field in question document examination for looking at the discrimination of inks. But it's not so widely used, or hasn't traditionally been so widely used, within fingerprint laboratories for examination and or photography. And again, this type of imaging and searching requires an infrared sensitive capture in order to see the contrast between on the evidence which we're looking at. In this example, this is a visible image of blood on a black security jacket. But when viewed in the infrared, the black material reflects or transmits the infrared back to the camera, making it appear white, and the blood, or the hemoglobin inside the blood, absorbs the infrared, making it appear dark. Reflective infrared imaging is easily facilitated by illuminating the evidence with an IR light source. Typically we use 800 to 900 nanometers, and the differences in the infrared absorption and or reflectance create contrast between the finger mark and the background which it resides. In this example, the infrared is reflected by the surface but absorbed by the fingerprint, which makes the fingerprint appear dark on a white background. It's possible to improve the contrast on many common fingermark enhancement techniques. Things like powders, powder suspensions, VMD, small particle reagent, multi-metal deposition, single metal deposition, physical developer, Sudan black, and many others. The general rule of thumb is that anything which deposits a dark residue onto the fingermark generally tends to absorb in the infrared. Therefore, if we have a background which reflects the infrared, we can obtain some contrast and improve the clarity and the resolution of our enhanced fingermarks. In this example, we have a confectionery wrapper which has been treated with a black magnetic powder. In this example, we have a confectionery wrapper which has been dusted with black fingerprint powder. The fingermarks, or the developed fingermarks, absorb infrared light and the background reflects the infrared. So in the visible, we see the marks looking like this. But in the infrared, the background becomes significantly muted compared to the fingermark, which is absorbing the infrared incident light. And we can achieve an increased contrast between fingermark and background. Even small differences in the amount of infrared that's either reflected or absorbed may produce enough contrast to reveal fingerprints, meaning that dye staining, gel lifting, or complicated imaging processes need not happen. Typically, when thinking about sequential processing of fingermark evidence, we often tend to consider the fingermark which is being developed and how we can improve its contrast. So we are targeting the fingermark itself or the constituents within it. However, it's also important when we're thinking about reflective infrared and reflected ultraviolet examination to consider the actual properties of the substrate itself. Generally, organic materials tend to absorb infrared, so things like wood, fabrics, blood, gunshot residues, etc. And other surfaces, inorganic materials like metals, mirrors, inks, glass, plastics, tend to reflect or transmit infrared. And if we know this, then we can start to dictate and think about the fingermark enhancement process, which is going to give us ultimate contrast as the end result. Another thing to consider when imaging in the infrared is the ability to view infrared fluorescence. Most fingerprint photographers and examiners will have used fluorescent treatments in the past, whether that be fluorescent powders or fluorescent dye stains, or even the use of high intensity light sources to look at the fluorescence from latent or contaminated fingermarks. In these instances, treated evidence is excited at a certain narrowband wavelength, and the fluorescence is emitted at a longer wavelength in the visible part of the spectrum. However, colourful, busy, patterned, or even reflective backgrounds often hide and mask or quench the fluorescence of the developing reagent. And so in this example, the fingermark is hard to distinguish from the background on which it's sitting. Now in 2014 to 2015, Foster and Freeman set out to develop a new fingermark enhancement procedure that would allow us, or at least aid us, in eliminating background interference and enhancing the visibility of fingermarks. And the reason that this was done was because the UK was starting to develop polymer banknotes, and of course polymer banknotes have got extremely patterned and highly fluorescent background artifacts that are embedded within it to aid in security discrimination. The research that was done over 2 years led us to the development of two infrared fluorescent fingerprint powders, FP Natural 1 and FP Natural 2. Both materials are non-toxic and are the first materials on the commercial market to have infrared fluorescent properties within the forensic field. The same principle can be followed as for standard visible fluorescent powders, whereby the powder is dusted onto a surface, any background material is wiped away, and the fluorescence in this instance, however, is emitted beyond the range of human vision in the near infrared part of the spectrum. To give a brief overview of the two powders, FP Natural 1 is green in appearance, FP Natural 2 is blue. Both powders can be illuminated with a red light source. FP Natural 1 can also be illuminated with a blue light source, and intriguingly, FP Natural 2 can also be illuminated with a near-infrared 780 nanometer light source. Their emission spectra are as shown on the screen. FP Natural 1 typically emits from about 715 to 850 nanometers, and FP Natural 2 emits from about 850 nanometers through to about 1000 nanometers. FP Natural powders can be used as a standalone process, but they're also ideal for sequential treatment. So after cyanoacrylate fuming, for example, the powders have been developed with such a particle size and particle morphology that they adhere very well to the three-dimensional structure formed from the cyanoacrylate residue. The infrared fluorescence that they possess allows us to both suppress background fluorescence, which is typical within the visible part of the spectrum, but also suppress background interference from artifacts such as reflections. They're low cost, they're non-toxic, and they're very simple to use, and we've proven excellent results on many substrate types. In this example, we've taken two Canadian $10 polymer banknotes and treated one with FP Natural 1 and the other with FP Natural 2. Both powders have produced excellent results, but the higher filter waveband used for FP Natural 2 shows how it can further suppress background interference. As briefly mentioned, FP Natural powders may be applied post-fuming in order to reveal finger marks on surfaces that traditional fingerprint powders or cyanoacrylate on its own may have difficulty with. In this example, we have some cyanoacrylate fumed finger marks on a metal bar. The white light image shows a heavy reflection running across the center of the photo, caused by the polished nature of the metal in question, as well as the incident light, causing the reflection to come back into the camera. Although some of this can be subdued with cross-polarization, it's very difficult to remove the reflection entirely. If we dust the cyanoacrylate fumed finger mark with FP Natural 2, illuminate it with our IR780 light source, and then look at the fluorescence from about 850 nanometers, we can see that we get high quality finger mark on a background which has no reflections interfering with it. So we're now going to go through a brief overview of a typical cyanoacrylate fuming process. In this case, we're using our MVC 1000 XL fuming cabinet. The process is initiated by taking the instrument out of standby mode. We can now open the door to load our evidence. In this instance, we're going to remove the internal shelf. This will allow us to suspend larger evidence types within the chamber on the sliding hanging rail located towards the top of the instrument. The laboratory technician can use our evidence hanging clips to safely secure evidence types onto the hanging rail, and then load freestanding evidence such as the wine bottle and the drinks can onto the base of the instrument. We now need to add our developing reagent of choice to our aluminium foil dishes, either cyano-bloom, our liquid ethyl 2 cyanoacrylate, or polycyano UV, our powdered one-step fluorescent cyanoacrylate material. After selecting our developing reagent of choice, in this case cyano-bloom, we need to ensure that the surface of the foil dish is evenly covered and distributed with the cyano-bloom itself. It can then be placed onto the hot plate within the chamber and secured using the weighted ring. The final step is to ensure that the water reservoir is topped up so that the humidity within the chamber can be reached in an efficient manner. With the evidence in situ and the cyanoacrylate reagent in place and our water reservoir topped up, we can now close the door, ready to begin the fuming process. The MVC product range of cabinets can be operated in both automatic and manual modes. Each of the parameters within the chamber can be changed to the user's preferences, but the standard set points are as shown: a humidity of 80%, a humidification time of 10 minutes, a glue temperature of 120 degrees for cyano bloom and 230 degrees for polycyano UV, a glue time of typically 10 minutes, a hold time, which in this instance is 0, and for cabinets that are equipped with the optional UVC tubes, we can set the UVC irradiation time accordingly. UVC is used to decontaminate the cabinets from DNA following each cycle. We are now going to process our evidence using the auto cycle mode. The MVC 1000 XL cabinet has integrated LED illumination at both the top and the side of the cabinet, allowing even light distribution so that the end user can monitor the development of the finger marks on the evidence. Now that the cycle has completed, we can open the door and remove our evidence for examination on the MLD, followed by the DCS5. Following cyanoacrylate fuming, and without the need for any further processing such as dye staining or powdering, the evidence can be located underneath the MLD. It can now be examined simultaneously in both the reflected ultraviolet and the reflected infrared. The image is displayed on the large live monitor feed. To help improve contrast where necessary, the oblique UV sidebar can be lowered. Examination of the evidence is facilitated with either the use of hand controls on the top of the instrument or foot pedals. The focus, focal window and capture of the images can be easily executed using both methods. As the examination is searched, the reflected UV image appears on the left of the screen and the reflected infrared image appears on the right hand side of the screen. In this instance, we can see that there's no benefit to the reflected infrared image, but the cyanoacrylate fumed finger mark is appearing as bright white ridges against a muted background on the left hand side of the image. We can now enlarge the window pane to look at this in full screen mode and analyse the detail of our developed finger mark. There are some simple image enhancement features within the software that allow the contrast to be changed and the image to be inverted where necessary. The finger mark can now be marked up and an image can be captured for record. The evidence is then taken over to the DCS5 for high resolution image capture and APHIS submission. Our evidence can now be examined on the DCS5, first using traditional white light illumination. The poor contrast between the finger mark and the background on which it resides would typically mean that evidence such as this would need to be reprocessed using a dye stain or a fluorescent powder. In this instance, however, we're now going to look at the evidence under reflective UV as we did on the MLD, but this time using the 20 megapixel high resolution DCS5 camera. Our 8x4 Mark II can be removed. The visible pass filter can be unclipped from its magnetic attachment, and our UV short pass Barda filter can be magnetically clipped into place. The combination of a quartz lens short pass UV Barda filter and our 82S handheld 365 nanometer UV light source allows a high resolution reflective UV image of the cyanoacrylate finger mark to be easily obtained on the DCS5. Significant time can be saved when processing evidence in this way. Evidence that's been treated with the one-step fluorescent polycyano UV is first examined under conventional white light illumination. If a suitable finger mark appears, the image can be captured. However, the fluorescent nature of polycyano UV means that UV excitation can allow for greater contrast to be achieved. A 365 nanometer UV light source is switched on. A 420 nanometer long pass camera filter is slid into place, and the lights are turned off in the room. The fluorescent output of the polycyano UV can then be captured on our DCS5. The frequency and regularity of cyanoacrylate fumed evidence in laboratories around the world makes it a fundamentally important process to really try to optimise the efficiency of recovering finger mark evidence. There isn't really a one-size-fits-all workflow that we can go to every single time to ensure we're going to get every single finger mark on the evidence which we have. We need to use combinations of white light illumination, dye staining, fingerprint powders, and now reflective ultraviolet, reflective infrared, and even infrared fluorescence to really try to maximise and optimise the amount of finger marks that we can develop. The advantage of the processes which we've covered and discussed today are that they're non-destructive to the evidence. We're not using shortwave ultraviolet illumination. We're not likely to degrade DNA. We're looking at processes that can precede dye staining and hopefully stop the workflow at that stage, whereby we can actually see the finger marks at that stage and don't need to move forward the dye staining process, thereby saving us time and easing the backlog within the fingerprint laboratory.